All right, our next presentation is by Daniel Pastor from the University of Strathclyde, and he is going to talk about how mosquitoes can inspire the next generation of sensors.
So, hello everyone. Thank you for the presential person and the live person to being here hearing me. As Hannah commented, I'm Daniel Pastor. I'm first-year PhD student of the University of Strathclyde under the supervision of Professor James Whitmill and Dr. Andrew Baxter-Reed. And I'd like to commend you our last work that is called Listening Like a Mosquito, a New Way to Amplify Sound. Maybe some of you is falling to your mind one question, and to be honest, I don't use that because it happened to me also, is why mosquito? Mosquito is an insect that make very annoying noise and also bite you and take your blood. And also, they can transfer some diseases like malaria or something like that. So why mosquito? So, and why create sensors inspiring mosquitoes? So why we create sensors? Because nowadays, if we think in sensors that are going to be used for biomedical application, we need to rely on sensors that need to have very high sensitivity and also very low power consumption. So what's missing today? What's the sensor that we have today? Today we have solution to make that. We have sensors that have very nice sensitivity, but they have a problem. So they use very complex circuitry to achieve the amplification process, and also they rely in very complex signal processing algorithm, but is made by some electronic devices. And this increases just the cost and also the dimension of the device. So how we can make it smaller, low power consumption, and more powerful? So we need to think in nature. Nature can give us a very nice inspiration to create very nice solution with very efficient solution for this type of problems. In that case, we use mosquito. So what's the difference of the mosquitoes with different animals or with us that we use membranes as eardrums? They use antenna. So the antenna is just a segmented structure, this segmentation that you can see in that image that is made with rigid segments and soft junctions allow they to have a very dynamic range for some certain frequencies just to be able to hear the female one up to 10 meters because they are able to amplify signals, very weak signals. So also they have this plumose antenna that is most common in the male ones that they allow to have more surface just to have better sensitivity to the viscous drag. So if we can see here, also for a very particular specimen of mosquito that is called Aedes aegypti, for the male one and the female one, the frequency response. So if we can hear what the sound they hear, for example, for the male one is, and for the female one, as you can see, it's very annoying, but they can hear and they can make coupling relationship just to be more and more. So our approach is try to use this structure that is very interesting in the animal world, that is the flagellum with the pedicel and the Johnston organ to create amplification. So our approach is just not try to copy the structure or the real procedure that they make to create amplification. Is just to use the physical principle of the segmented antenna to have frequency selectivity and also amplification, so we can achieve this amplification in a passive way and not in an active way. So in our case, we use a substrate where in the first second mode, in the antinodal zone, we put a cantilever synchronized at the same frequency just to achieve model splitting, do very strong coupling. And in the junction between the cantilever and the substrate, we are going to have the best energy transfer. So in that particular part, we are going to achieve the most energy just to be able to have a very powerful signal and not a weak one. So the substrate is working as the flagellum, so it's able to take the vibration for the surrounding fluid. In that case, it's particle motion, not pressure gradient, not pressure like in eardrums. And the cantilever as the scolopedia or the mechanosensory unit that is located in the Johnston organ, that is just flexible elements that are able to amplify the oscillation with producing self-oscillation in phase. And the junction at the pedicel, that is the zone where is located this Johnston organ, that is just the connection between the flagellum and the pedicel when the magic happens. So how we did this study? The first thing that we have made is just make a mathematical model just to see if we are going to achieve good results for that structure, that particular structure. And we can see in the plot the two peaks due to the modal coupling, and is the less frequency one is the in-phase mode when both structures moves at the same phase at the same time, and the red one is just the anti-phase one, is when the structures move in at different times. Later, we perform a computer simulation based in finite element models just to achieve better results and see if we are in agreement with the analytical model. And we are able to compare the results with very known scientific studies. In that particular case, we can see that we are achieving less than 5% of error, so we are in agreement and our system is really working. We fabricated this with 3D printing, just with digital-like processing printing with our Asigamax printers, as you can see the devices here. And the measurements is just make it with a laser technology with a sound field known by a loudspeaker. So the results of our work is just letting physics do the work. So we are achieving very high mechanical amplification just in a passive way, up to temper amplification that is translated to 22 dB of gain for more of the scientific person here. But the good and interesting thing is with no external power supply. So imagine that you can hear this with a normal sensor, but with our approach we can hear just the structure. So why it matters? Why this sensor or this new technology is important? So we can make some potential application is make the devices smaller because the companies think about that and needs that. We can make more efficient and we can make no power needed. So our signal to noise ratio is going to be greater. And the application that we think for that devices is just make medical devices like hearing device or cochlear implants with low power electronics. So thank you so much for your attention. If you have any question, I'm here and happy to answer that.
Yeah, we'll take a room question first. You don't mind passing the mic?
Yeah, thank you. What kind of bandwidth do these antennas have, your amplification system?
In our system, it's just in the two different modes that you are seeing, the in-phase and the out-of-phase one. So the bandwidth is very narrow. So our next steps is just try to use the higher modes of the substrate and put in the antinodal zone of that substrate cantilever syntonize at that frequency just to have more broadband signal. Yeah.
We have a question from the live stream. Let's see. This one's from Avery. Avery asks, do you have any ideas for how to further increase the sensitivity of your device?
Yes, exactly. If we think in nature and the real antenna, we can make some plumose structure or try to play with the geometry, just with the relation between the thickness and the length and the width, just to allow to have more surface to increase the sensitivity to the signal. So yes, it's possible, yeah.
We have just a couple more. The next one is from Frank. What are the biggest remaining hurdles before these bio-inspired passive sensors can compete with today's electronic sensor technologies?
Yes, very interesting question, because this is a question that I make to myself also. So we are just thinking because the most important application of our goal is to create a cochlear implant, and some people with that disease, like the image of this kid, needs to reply the batteries, needs to charge it, and also they have problems because another kids can see it and they can talk or loud about that. So I think it's just it's a very good technology just to solve that problem and perform better quality of life to that type of person.
Thank you. And we have one last one, just for fun. Are there other creatures you can look to for further inspiration?
Yeah, there are a lot. For example, I was working also in some parasitoid flies that is called Ormiacracea, that they have, for half directivity, humans, we have a certain distance, so we can have interaural difference between the ears and we can know the location of the sound. So, but this is due, we have a certain distance that is comparable to the wavelength. In the case of that fly, they have two eardrums that are very near each other's, is 350 micron more or less. So the time is almost the same for the sound to came to both eardrums. So how we can explain that this fly have the most accurate directive response in the animal world is because they have the interpanel bridge that couples the membrane, and with the bending and the rocking mode, they are able to increase this interaural difference and have 2 degree of accurate of directive response. And also they have corrugations in the eardrums that allow to increase that more. So we can see in a lot of insects to have inspiration for different features like directivity, amplification, tonotopy, or frequency selectivity.